Well, greetings out there in YouTube land and welcome to today's new video. It's going to feature a very unusual and very old amp, and it's exactly the type of amplifier that I have come to really appreciate. It's rather compact. It's only 19 inches by 13 inches. I know it's hard to tell in an image like this with nothing relative to compare it to, but fairly lightweight, and it appears to feature two 8-inch speakers. It's called a Stewart, which is a brand I am completely unfamiliar with. Some of you may have heard of it. If so, please tell us about that in the comments. I will go in shortly and do some research on the computer to see what we can find. Also, I'll look for a schematic, but let's not keep our fingers crossed on that one. This was one of several amps that have been sent to me by the same viewer who lives in California. He's a harmonica player, and you know how harmonica players dearly love amps like this, which have two 8-inch speakers. He's asked me to go through this and make it work just as good as new, if not better. And that's what we'll do. Also, it'll give us a rare opportunity to examine every detail of the construction and design of this amp and to learn something about a rather obscure brand and maybe learn something while we're repairing the circuit. Okay, if that sounds appealing, we're just about ready to take this apart and see what makes it tick. Well, with all the kidding around in a previous video about killer winter storms, looks like we really had one. Okay, we got probably a good 1/2 to 3/4 of an inch of snow. There are rumors that there are drifts up to 2 inches deep. Okay, I know this is a frightening prospect, but hopefully we'll be able to put on the snowshoes and trudge to the store and get provisions and survive it. Okay, so stay tuned. Well, as is so often the case here in the great Southwest, 2 hours later and there's not a trace of snow. Okay, so I guess we'll be able to take off the snowshoes and get back to living a normal life. Okay, I'll use my hand here for comparison, give you an idea just how compact this is. It has a really nice kind of beigey, leathery looking front here with the Stewart decal, off center too, quaintly. And the wraparound material is contrasting and has a very interesting grain to it. Looks like the handle's been replaced, but with a really nice one. And overall, the condition cosmetically here on the outside, grill cloth, covering material, everything is darn near perfect. Okay, let's turn it around and see what the back looks like. It's got a really nice looking control panel here with 3 instrument inputs for studio. Nice knobs. I'd never seen knobs like this on an amp before. That are volume and tone. We don't care about that stinking treble. All we care about is bass. Okay, the Stewart brand logo here proudly emblazoned. 117 volts, 60 cycles, so obviously made for the United States. Looks like we got more packing material. Let's remove the screws, pull the back panel, and see what waits us inside. Okay, the back panel is off. I haven't removed the packing material yet, but I was greeted when I pulled the panel with a 12AX7 coming out, rolling off the table, and I had, thank God, with my lightning fast cat-like reflexes, caught it in midair. It's a Sylvania 12AX7. So let's very carefully unpack this and see if any other surprises await us. Okay, all the packing material's out. We see we still have the original 2-prong power cord. Mysterious hooks on either side for reasons unfathomable to us mere mortals. Looks like the two 8-inch speakers, one is nicely wired up and the other one has No connections at all, with only one wire evident. That should be exciting. Okay, let's lay it down and try to figure out what the tube complement is. For an amp this old, this one is just immaculate inside. I see no paperwork or anything like that to help us tell where it was made, or to even tell us the position of the tubes. So as I extract them from their sockets, I'm going to have to make a diagram. Make sure we get them back in the right order. 12AX7 came out of this little socket. I'm looking at the speakers, and this one is held in only by 2 screws. It's a little bit loose, and it makes me nervous. It's in a different rotation than this one. Of course, this one seems to have the output transformer attached, so that's probably why it had to be rotated. But I'm hoping that there's nothing wrong with this speaker. You notice the 3.2 ohm. They may well be in series, okay, for about 8 ohms of impedance. If they're in parallel, God help us, on the output transformer. Also, it kind of appears to me that that may be the output transformer, but we'll see. I also don't see a power transformer. Okay, so all sorts of mysteries here. So let's go ahead and pull the tubes, make note of what they are and where they're located, and then we'll pull the chassis. Well, I'm just a tiny bit disappointed to see that the tubes are 12AX7, 250L6s, and a mystery tube that has no markings, probably a 35Z rectifier. We may well have push-pull 50L6s here. That would be unique. But anyway, it's obviously a series filament circuit. But let's let that not deter us from our mission to make this beast work and sound just as good as it possibly can. Okay, I notice also that the output transformer is not attached to the basket at all, but to the chassis. So the question still arises, why was this speaker removed? Okay, and why is it not wired in? Okay, we'll try to solve that. Let's go ahead and remove the screws and get the chassis out and take a look at it. Well, I located that second missing speaker wire. It was tucked in underneath here. And doing a little forensic recreation, you can tell that with the position of these 2 wires that at one time this speaker was rotated, what, probably 30, 40 degrees counterclockwise to be the mirror image of this one. Once again though, why was it removed? Why was it disconnected? Why was it put back in wrong? Okay, so these are just some of the mysteries we'll try to solve then as we delve into the mighty Stewart amplifier. And one other observation. Looking at this, you can see that the 2 wires are coming here from an output transformer. One comes over to this speaker, then we jump over to this one, and then we return over here. Obviously then they are in series, so we will have 8 ohms then of speaker impedance. Thank heavens, because like a 2 ohm output transformer seems a little unlikely in an amp like this. Well, the chassis is out, and one of those grand discoveries is that the original shredded handle is stuffed into the speaker basket. Hopefully it didn't hurt the cone. Okay, you never know what you're going to find when you open one of these things up. Okay, so let's go ahead and pull these speakers and take a look at them, test the voice coils for continuity, and try to figure out what's going on. Well, looking in here at the speakers, it's obvious they are completely mismatched. They're both 8-inch, but other than that, they have nothing in common. The speaker cone ribbing is completely different. The baskets are completely different. They're both Alnico. This one is 3.2 ohms, and I'm not sure about this one. Let's check its DC resistance and see if they're also mismatched as far as impedance. Well, the left-hand speaker said 3.2 ohms. That is impedance. The DC resistance should be a little less, and it is. It's around 2.9 to 3. So apparently the voice coil is intact and it is properly marked. Now the DC resistance of the right-hand speaker is much higher, 4.1 ohms, which means that its impedance is probably more like about 4.8 or 5 ohms, considerably higher than its partner. Now mismatched speakers like this can actually give you some great tone. Okay, in fact, I almost advocate in any speaker cabinet, why put in two identical speakers which are just going to more or less reiterate each other? Why not have a difference between them, even an Alnico and a ceramic speaker, so that you get kind of the best of both worlds, okay, and a really nice sort of harmonic tone. But when you have mismatched impedance, that creates an issue. Now let's discuss that briefly. Using the trusty audio signal generator, I'm going to output the same tone to both of these speakers. Let's see how it sounds. Do they put out about the same volume and quality of tone? Let's see. Okay, let me crank up the volume here on the signal generator. Okay, now pay attention to the quality of the tone and the amplitude or volume of it. Okay, now I'm going to switch over to the other speaker. God, you can barely hear it. Much lower volume. Now that has to do both with the impedance and also the efficiency of the speaker. But as you can see, trying to use this pair, say in parallel, all you'd hear is this one. This one would be whispering in the background. Let's hook them up in series and see what happens. Okay, I flipped them over where we can gain access to the cone to make good comparisons. They're wired in series. I'm going to input the same volume tone now to the two speakers in series. We'll go into this one. Notice it's not as loud, it's diminished somewhat because now the series resistance of the voice coils is greater, which will attenuate the current flow. To me, the volumes sound identical. So it would appear then that you can have mismatched impedance speakers if you wire them in series rather than in parallel. Okay, so this pair may be okay. We'll see how they sound later during the audio demonstration. Doing a little further checking here, this is the right-hand higher impedance speaker. I'm hearing a lot of voice coil rubbing. I don't think this speaker is going to work well. We'll see in the audio check, but I have a feeling this one's going to sound lousy. Okay? Well, so far so good until we flip over the chassis, and then we're glad we didn't just recently eat lunch, okay? Because it is a wiring disaster. Okay, we've got capacitors flapping in the breeze, selenium rectifiers, God help us, okay, and no schematic, of course. And we're left to wonder why it has a small transformer and a larger transformer. Now granted, one of these is going to be the output transformer, probably this one over here. But is this, what, a filter choke? I guess I'm going to have to draw up the circuit, or what we have of it to draw, and try to figure it out. Okay, this is a fine piece of architecture here. Okay, the ancient Romans and Greeks would have paid a fortune to be able to duplicate this as the foundation for their buildings. Okay, enough insults. Also, I noticed something else. I've never seen copper contacts for the input jacks. Okay, these are not self-grounding. They're very crude, very basic, and I've never seen an American amp that has anything like this in it. I'm beginning to wonder if this may have been made somewhere outside of the borders of the United States and imported. Okay, you got to agree. Have you ever seen anything like that? I never have. Okay, let's take some Dramamines and start trying to plot this semi-wretched circuit with two 50L6s, a mystery tube, we have no idea what it is, and a transformer that makes a little sense. And of course no schematic. Okay, so let's get started. Now here on a site called Bing.com is exactly the same amplifier. It says rare 50s vintage Stewart amplifier, but of course there's no information when you check on a view page or view image. No information is forthcoming. But at least we know that the one we have is not unique unless it is this particular one right here. And here is a very interesting SS Stewart amp that I found on Pinterest. There are no details about it, and the fact that it emphasizes the SS before the Stewart makes me think this may be a different manufacturer than the one who made the amp that we're going to work on. Now here is a Craigslist ad from 10 years ago, okay, 2010, listing a rare Stewart tube amp for sale. And this may explain why I have never encountered this brand before, because they say it is British made. Okay, we'll check inside the cabinet and on the chassis and offer any evidence of this. But if it is European, that may explain why I have never encountered one here in the United States. As we will see, the amp that we're going to work on, it has two 8-inch speakers, and if I roll down here a little bit, you'll see that this one also has two 8-inch speakers and has a 12-watt output, they claim. And I think that's just too much of a coincidence not to mean that this amp and the one we're working on were made by the same company. Okay, so that helps. It's British, it's uncommon, especially in the United States, and they tended to favor two 8-inch speakers. Also, if you look real close at the logo, the font and color of the letters is exactly like the amp that we're working on. So I have no doubt that what we have out in the workshop is a British-made Stewart amplifier. Naturally, there are absolutely no schematic diagrams offered for vintage Stewart amps, but that's not really a problem. I'm used to that. In fact, anymore I tend to just work off the circuit itself rather than schematic, because many times, if you can even find the schematic, it may not be accurate for the circuit that you're working on. Okay, so we're on our own with this one, which is just fine. So let's get started. Let's take a few moments to have a brief discussion about how series filament amps are designed and why so many people hold them in low esteem. First off, in what I would call a normal amplifier circuit, which has a power transformer, which the series filament amps do not. The power transformer provides isolation between the primary AC circuit that you plug into the wall and the entire amplifier circuit. From this point forward, there is no connection to the wall AC receptacle power. Now for comparison, let's look at a fairly generic series filament circuit. In this case, a Silvertone 1448. They probably sold 1 million of them, okay? Now, what's shocking, literally, about this design is, notice these are the two AC wires that come in. There is no power transformer here. It has a little 6-volt transformer for the 12, in this case, AU6. Our amp that we're working on today has that little transformer for the 12AX7. But for all the rest of the power in the amp, there is no power transformer. Here's how it works. Two AC wires come in. One of them comes up here to the plate, okay, and the other one comes down here. Now you notice that this is going to be our filaments here in series, hence the name series filament. The AC is going to run right through the filaments of the tubes, and the transformer primary for the 12AU7. But look what happens afterwards. It keeps running down here, and this wire goes to the chassis. Now yes, there is a 0.05 microfarad cap right here that theoretically will not pass 60 cycle AC to the chassis. But after this cap is about 40 or 50 years old, though, do you want to state your life on it? Okay, so also you notice it's bypassed by a resistor. So here comes your full wall AC, and you have this rather puny defense here for it to go right to the chassis. Now here's the real scary part. This isn't a polarized plug. Okay, now 50% of the time you're going to plug it in, and the hot wire, the black one's going to come up here to the plate, okay, and then down here to the return. But the other 50% of the time, that's the hot wire, right in here and right to the chassis. So also you notice the chassis comes up here to the ground for your instrument cable to plug in, and then goes right to the metal parts of the guitar or microphone or harmonica, whatever you're holding. So you can see why people are nervous about these, and I am too. I don't routinely work on any series filament amps. The owner of the amp who sent this to me confessed he didn't know it was series filament and wouldn't have sent it if he did. I'm going to do the best I can on this to make it safe, but I'm just telling you, just warning you, okay, you can put a 3-wire power cord in here, and it would help because then you would have your chassis grounded, and that would make a difference. But once again, do you really want to flip a coin and take a chance? Okay, I'm going to do my best with this one because it was sent to me and he wants it fixed. So let's see how we can do that. Well, I've been studying the circuit here for an hour or two and drawing up a basic diagram, and I made a couple observations. This smaller transformer that was questionable is a dedicated 6-volt filament transformer for the pilot light and for the center tapped filament of the 12AX7. Okay, so that mystery has been solved. Now, since the 12AX7 has its own dedicated filament transformer, that leaves these 3 tubes here to have their filaments in series. 50L6, 50L6, and I believe a 35Z4. Remember, the tube was not marked. Now, the output from the 50L6s is in parallel, but the filaments are in series. Now here's just a simplified drawing of how the series filament circuit looks. We're going to plug in to 120 volts AC, and each of the filaments will drop this amount of voltage. It's the first 2 numbers in the tube name. Okay, so the rectifier is going to drop 35, then 50, then 50. And as you can see, the return here will be 0. Okay, you can't drop more than you have. Well, I removed that giant can cap and have soldered in a radial 40 microfarad cap in its place. I thought this was the best configuration. Alright, I removed the leads from that isolated 4040 capacitor and replaced the screen voltage dropping resistor with a higher wattage one right here. This one was way out of spec, and as you can see, I have 40 and 40, and these are at 450. I didn't have any of the lower voltage capacitors, so these should surely be up to the challenges here of the series filament circuit. So this capacitor has been replaced, the wobbly one out here has been replaced. I'll show you a diagram here in a few minutes, but for now let me just briefly explain. I'm going to run the 120 volts AC through the filaments of the three tubes so that we get the voltage drop across them. And we have to have energized filaments for these two tubes, the 50L6s, to work. Okay, but I'm going to create a completely separate B plus circuit for our plates and cathodes. To do that, I will not be using the rectifier tube or the selenium rectifier. I'm going to install a full wave bridge rectifier for the B plus DC. So I'll be keeping the 6-volt dedicated filament transformer for the 12AX7. I will be retaining the series filament circuit here using the wall AC voltage, but I'm going to be removing that selenium rectifier and not using the 35Z4 as for rectification for the B+. The B+ is going to be coming out of the little full wave bridge rectifier I just showed you. Now let's wire our B+ circuit. You can see from our full wave bridge rectifier here, the little squigglies at the bottom left and top right show that the AC goes there. Polarity, of course, doesn't matter. And we're going to have positive out of that faceted corner and negative out of the pointed corner. This particular full wave bridge rectifier is rated at 400 volts, which is about 3 times what it will ever see, and 3 amps, which is going to be more than plenty to cope with these tube plates. Okay, these are in milliamps, so it's way overrated, which is the way you want it. Okay, let's look now at the wiring of the full wave bridge rectifier. You see that the AC goes to the 2 squiggly corners, and those squiggly corners are right here and here. This one is connected to one end of the AC, and this one down here is connected to the other end of the AC. So when we turn the switch on, we not only energize all of 3 of our filaments in our series tubes, we energize the transformer for our 12AX7, and we're going to energize the full wave bridge rectifier. And we see that the B plus is going to come out of this corner and the B minus is going to come out of the other. If you look here, you see the plus, and I have wired it to this terminal right here, and the minus is going to be right next to it right here. So now it's time to run from here and wire all of our tube plates and screens, and then the cathodes will all be wired to the B minus down here, this one. Okay, also all our filter capacitors will be between the B plus wire here and the B minus wire here. We'll see this again. I'll show you in just a few minutes, and it'll be made clearer once you see how it looks in the circuit. Okay, now it's time to wire the tube plates with the B plus. I made this diagram fairly simple so that it would resemble the filament diagram, and I left off one small detail, and that is the B plus does not go directly to the 50L6 tube plates. It's going to have to run through the primary winding of the output transformer. Okay, so that's just a minor complication. The 12AX7 plates will not go through the output transformer, so we will be wiring the B plus directly to them. Now I've connected the positive DC output from the full wave bridge rectifier over here to the primary of the output transformer. Okay, then the other end comes up and goes to the 2 plates on the 50L6s. So those plates are wired. Next we have to provide B plus of the proper voltage to the 2 plates of the 12AX7. Now that we have the B plus going up through the primary of the output transformer to the plates of the 50L6s, let's put in the filter cap. This will be the reservoir or first filter cap, and it'll be from the B plus to the what we'll call B minus, which is really the negative DC coming out of that full wave bridge rectifier. Okay, and here it is right here. I've got one wire On the negative side going to the B minus, and on the other side I have a wire from the positive lug over to the B plus. I'm already getting ready now to wire the screens, and we're going to go here. The voltage will be dropped by this 4.7K resistor, and now this will be the second filter cap over here, and I'll draw a little diagram for you, but we're going to drop the voltage and then send it to the screens of the 50L6s. Okay, here's a quick diagram. As you can see, I've added in the 4.7K resistor you just saw. We'll go to our second filter cap, another 40 microfarad, and these are at 450 volts. I didn't have any of the lower voltage caps on hand, and it will come up and connect to the screens of the 50L6s. Okay, now we have our slightly dropped B plus over here going to pin 4 and pin 4, which are the screens of the 50L6s. Well, welcome back to Chapter 2 of the Nightmare on YouTube Street, in which after quite a few hours of modifying the Stewart series filament power transformerless circuit, remember the double-ended 50L6s and all, I'm talking hours here. The end result just stank, okay? Tone was lousy, volume was inadequate, and there was a hum I could not get rid of. Not only that, but bear in mind this is for a professional musician. Now, he's going to take this probably out to performances, plug it in with the series filament circuit, about, you know, a chance of getting electrocuted, and then lousy tone, and they're going to say, where did you get that crappy amp? And they'll say, oh, Uncle Doug rebuilt this for me. Okay, so rather than take that risk, okay, now believe me, it crossed my mind after all this work, just send it this way and charge accordingly and wish him the best. Okay, but to be honest, I can't do it. Okay, both for the good of the customer and for my reputation. So I did what I had to do, and that is I completely gutted all of the work that I had done, and I decided to scratch build a circuit that I knew would work, would sound great, and would be safe. So let me show you how I did that. First off, I installed a proper power transformer. Okay, I don't think I will ever work on another series filament circuit, either for myself or for a customer. There are just too many draws. First off, this is about a 375/375 power transformer, which provides output voltage once it's rectified and smoothed to its peak will be way too high for the circuit I have in mind. Okay, so I'll show you how I brought it down to below 500 volts of the initial inrush voltage. Okay, now when you're using 450 volt rated caps, you just cannot have an inrush voltage that's like 550 volts. Okay, so I'll show you how I tame this beast. Secondly, it does not have a center tapped high voltage output, which means you cannot use full wave rectification because you have no center tap to ground. So it also does not have a 5 volt output winding, so I cannot use a tube rectifier. That's two reasons I can't. So I had to go with a full wave bridge rectifier. And on the plus side, it has a good stout 6.3 volt filament output. Okay, let's look up here at the top of the circuit and see how problems were resolved. First off, I thought I'd build him a 5C1 champ, okay, a nice tweed champ, warm, mellow, vintage tone, 6SJ7 preamp tube. I went ahead and built this whole thing, and it sounded good, but it had inadequate volume. Bear in mind, this guy is going to be performing, and this amp has to be able to make itself heard. So after quite a few hours of building this circuit, inadequate volume, decided to scrap it. So I decided to try a Fender Princeton 5F2A. Now, some of you Princeton fans know they started out with a single-ended Princeton. It's really a 5F1 champ with a tone control. And I thought, why not? You know, let's give this one a try. I've built one of these in the past. I have a video of the result, and it just turned out great. So, after scrapping my 5C1 plan, I went with a 5F2A. Let me show you how it turned out. I wanted to use my little block full-wave bridge rectifier, but it was only rated to 400 volts. And as we see, this is going to have to face about 500 when it's first turned on. So you can see that I went with high voltage and fairly high amperage. These are 1000 volt 3 amp diodes, and I built my own full wave bridge. Instead of it being in a normal square shape, I bent this end up for clearance over here with the cabinet. Now, because the output from this full wave bridge is going to be well over 500 volts when this is first turned on, I had to tame that a bit to keep it under 500. So I put right here in series what is this, maybe a 3 or 4 watt 1200 ohm resistor. So the B plus that's usable will come out right here at the end of that resistor lead. Let's look at the schematic. You'll see here's where the B plus comes out with that 1.2K resistor, keeping the voltage down to reasonable levels. I left off one of the 16 microfarad filter caps. I didn't think it was necessary. To create this 16 here, I used 2 10s in parallel, and then the B plus will come up here to the output transformer primary and then to the plate of the 6V6. And here it comes right here to the output transformer primary and then to the plate of the 6V6. Then we go through a 10K resistor to drop the voltage down for our screens. It should be noted that since I'm doing a full wave bridge rectifier, I have no need for a rectifier, so this socket is unused. Also, this socket here will be unused. Remember, it was for the 1950L6, and I'm just using it like a terminal strip. Okay, here's the 12AX7 over here. We'll talk about that in a second. We see that our 6V6 is biased, they say at 470 ohms. I know from experience that it needs to be higher, and so I have put in here an 820 ohm bias resistor, and it is bypassed by a 25 microfarad bypass cap. We go through a 0.02 coupling cap into the first stage of our 12AX7. We see down here that after 22K voltage drop and an 8 microfarad filter, we're ready to provide our plate voltage for a 12AX7. Here we see the 22K resistor, and our plate voltage comes over here through 2 100K resistors to the plates. And there's an interstage volume and tone control, which are mounted up here. I had to go with new pots because the ones from the Stewart circuit, first off, the on-off switch here was junk. Even after I fixed it, it still was a little sloppy. So I've used new pots here and wired the proper volume and tone circuit. Since I'm not using that piggyback on-off switch, I installed an antique toggle switch that works perfectly and looks like it belongs on this control panel. Then we look here at the standard Fender input circuit with 68K resistors. I went with the self-grounding inputs to keep this thing quiet. If you remember, that Stewart had those wretched kind of corrugated copper ungrounded contacts. That was part of the hum problem. And you can see here that I have two of the standard Fender inputs, and then I went with kind of an oddball on the third one. I just put in a .01 microfarad cap. Now, and this is going to be used with a microphone, if the microphone happens to have its own power supply, there is a problem, and they found it on these early amps, that the input may have some DC that's going to come in here and alter the bias of the 12AX7. So they ran a capacitor right here. Now, it gives a sort of unusual tone, but I thought I'd throw that in. Just I had an extra input, and I thought I'd put that in there for a little novelty. All right, I've got it plugged into the current limiter. I have the 6V6 with the Eurotube's bias probe in series, so that we can check to be sure that we don't burn up the tube. I'm really not sure what the bias is going to be here. Hopefully it'll be at a tolerable level. I've also made some tape covers for the two unused tube sockets, just in case say this amp changed hands and somebody looked in here and thought, oh heck, I think I'll plug some more tubes in here, which wouldn't be good, okay? That is to discourage them. Okay, I just do the best I can. Next, I've got the output here that would normally go to those two 8-inch speakers in the cabinet, over here to a jack that connects to my 12-inch workshop speaker. And besides that new old toggle that I installed for the on-off, I also installed a new, proper, and somewhat aged fuse holder. Okay, we want this thing to be just as safe as possible. All right, let's turn it on and see what happens. Well, the pilot light works. Let's see if the amp starts amping. I've got the volume, no, not much. It's like about 1 out of 10. Look down here, and the ideal plate voltage on this circuit is a 350, and look at that. So it looks like that 1200 ohm resistor did its job. We're looking at about 30 milliamps of plate current. You know what is that, about 10.2 for plate dissipation? It's absolutely perfect. God, that's rare. Okay, and there's absolutely no sound from the shop speaker. It's dead quiet. In fact, I'm wondering if the amp is amping. Okay, let me short out one of these inputs. Oh yeah. Turn it up a little. Oh yeah, it sounds good. All right, let me hook up an out-of-tune guitar, for which I'm famous, and strum a few chords. When I switch it on, let's monitor that input voltage to see that it stays comfortably below 500 volts. Perfect. Some people aren't aware of that initial surge. You have to be careful with your filter cap voltage ratings. But look at that. Absolutely perfect bias on this. What's that going to be, about 10.2? Something like that, which is ideal. Thank God. Alright, as you can see, I've wired up the two 8-inch 4-ohm original speakers in series as they came, and brought the wires up here to a 1/4-inch jack. Now this will allow you to plug in the cabinet speakers for an 8-ohm impedance, or any sort of speaker cabinet or separate speaker that you want to connect. Now, considering the quality or lack thereof in these two 8-inch speakers, I have a feeling they're going to have a heck of a time coping with the power from this new circuit, even though it's a single-ended 6V6, okay, with what, 4 or 5 watts. But let's give them a try and see. Okay, we'll turn this around and play a few tunes, and then if it's as bad as I expect, we'll plug in a really good speaker and see how this new circuit really sounds. Okay, here we go with those original speakers. Ugh. Oh, that was ghastly. Obviously one or both of them are blown. It sounds like the voice coils are rubbing and they're just a mess. So let's unplug those wretched speakers and plug in a good one and see how this amp really sounds. Okay, here we are all set up with Jack and Ollie, the mighty Shure M57 microphone, and let's play a few tunes and see what you think. Well, I guess that's about it for this very lurid video depicting the trials and tribulations of those foolish enough to try to repair amplifiers. I could have edited out, I guess, some of the rough spots, but I just wanted you to see what it's like behind the scenes. Some of these jobs go smoothly and some don't, as you just saw. I wanted to take a few seconds here to show you some t-shirts I received recently. One from a friend of mine who made Doug's Hot Rod Shop t-shirt for me, showing that little 28 Model A pickup that I showed you in earlier videos. Here is one from my daughter to commemorate my trip a few months ago to Nashville, where I took you on a tour of a couple guitar and amplifier shops. This one is from the Speaker Exchange in gratitude for the favorable reviews I've given them and their products and my videos. And this last one is literally the shirt off my back. It's the one I was wearing this afternoon while making this video. And it's from a generous viewer in Newport, Rhode Island. So thank you, all of you. Now I'll be very stylish in what I wear, and I really do appreciate your kindness and thoughtfulness. And while I'm speaking of kindness and generosity, I wanted to give my traditional thank you to all my Patreon patrons and PayPal contributors. You're keeping us on the air and advertising free, and I want to tell you how much I appreciate it. If any of you would like to join them, I will put links in the video description to enable you to do so. Now for a second feature, I have something really special planned. First off, I'm going to show you step by step how the 3.2 carburetor modification was completed on that 1930 Ford. Then, as many of you have requested, I'm going to put the camera inside the car and we're going to go for a ride. And I'm going to, toward the end of the video, demonstrate what happens at 60 miles an hour when you're on the central two-barrel, and then step on the gas and open the two secondary carburetors. I think what you'll see and hear is rather exhilarating, and I'll show you the speedometer after we slow down a little bit, because I'm holding the camera with one hand and the steering wheel with the other, to tell you the truth, and it's pretty spooky. But anyway, I think you'll get a kick out of it. Hope so. And so thank you all for watching, for subscribing, for contributing, for writing such nice comments, and for caring. Okay, we hope to see you again in future videos. Bye for now from all of us here at Rusty's Workshop. And here's the 3.2 manifold installed, and as you can see, there's very little clearance back here between it and even this small distributor cap, so there's no way this thing could have fit with that giant HEI distributor. So there it is. It does fit. I was worried about it interfering up here, but no. It sits down nice and flat. So I guess now it's time to machine the manifold for vacuum lines, for the vacuum modulator to help the transmission shift, for vacuum advance, for the distributor, and then install it, and then start installing the carburetors and linkage. I thought a long time about where to put the vacuum ports in this adapter manifold. Now on the aluminum high-rise, that air gap manifold that's on the engine, there's really no accessible place, and you hate to drill because then some of the aluminum shavings will get into the engine. So what I've done is I drilled a hole here in a very thin area that's sort of out of where all the excitement's going to be taking place, and then I'm using some JB weld and pressing these little devices here that I made. I cut down. They normally have like a barb on either end of them, but I cut it down nice and short to where it was very unobtrusive. And I've already drilled a hole over here, and now I'm going to press this one, finish pressing it into place with the JB weld. That should give me good vacuum ports for the vacuum advance and for the vacuum modulator from the TH350 transmission. Well, I've been real busy assembling the carburetors, linkage, fuel inlets, intake manifold, and vacuum ports. As you can see, the linkage is progressive. You can just run off this middle two-barrel with that much travel, but then if you step a little harder, you see that those secondaries on the outside open, and you have to be sure they open all the way, and I'm assuming you're going to get quite a little boost in acceleration when that happens. Okay, so you can run around getting really good gas mileage with this much travel, or go a whole lot faster with that much. Looking good so far. I think it's time now to install this on the intake manifold and then start coming up with a fuel delivery system and also some way to connect to this with the accelerator pedal so it can be pulled smoothly. Well, it's a momentous occasion when the tri-power setup is finally attached to that air gap manifold. The vacuum lines are connected, and now it's time to fabricate a fuel delivery system, and also, and this is going to be challenging, accelerator linkage, which is totally safe. It won't bind, it won't stick. You really have to be careful. Okay, so that's the next step. I think this would be a really nice spot for that chrome fuel block to be installed. It's centrally located and can distribute fuel to each of the carburetors. It's going to be suspended about 2 inches then above the intake manifold, and is going to be the bracket is going to be held by these bolts right here. So I've started fabricating the bracket that will hold it. I need to do some finishing on the edges and corners and then bend it into shape, and I'll show it to you when that's done. Okay, here's the bracket all bent up and fit perfectly to the fuel block and painted semi-gloss black. Now it's time to attach the fuel block. I put in all of the little spouts that it needs to deliver fuel and to receive fuel. I'm going to install it on the bracket and then install the bracket on the engine. Alright, there's the fuel block installed on its platform, and now the hot setup on these old cars is to use this red neoprene tubing, and so I'm going to cut it to fit and then plumb the 3 carburetors. I'm waiting on a fuel pressure regulator that's going to be sitting right here before I can do the sort of the primary side here of the fuel delivery. I ordered it 9 days ago, and of course it's not here yet, but when it gets here it's going to sit right there. I also noticed that every single piece, every nut, bolt, washer, everything in this pile of parts that I ordered, even the air cleaners, is declared to cause cancer and reproductive harm in California. So I'm glad I don't live there because I'd probably have cancer by now. But anyway, it just seems really over the top. I mean, what are you going to do here? Get a pregnant woman to chew on this red hose? Come on, give me a break. And there is the red fuel line plumbed. Try to keep the curvatures consistent. Now it's time to focus on the accelerator linkage, and that's going to really be tricky. Okay, somehow it's going to reach in here, grab a hold of this arm here on the primary carburetor, and be able to pull it straight back without hitting anything that gets in the way. Now my initial plan is to use this polished 1/4-inch steel rod that I bent last night, and it can engage the holes in the primary arm there and come out the back, and I think be pulled by a cable that comes through the firewall right here. I'm going to try to kind of mock it up and see if there's a way I can do that without it pulling like this, you know, because this is not really lined up. This is more for a 4-barrel, whereas here we've got narrower tube arrows. So let's see what I can come up with. Okay, here's my plan. I've cut out a unusually shaped piece here of 1/8 inch cold roll steel, and as you can see there is a boss on the manifold back there and right here. And my plan is to have this bolt down securely, and then right here construct like a tower that comes up and will allow me to pull on that rod and the linkage back far enough that it can open all 6 of the butterflies, and then I'm going to use a cable that's going to come around like this and go in here. So it's going to come out, the cable will make a sort of a gentle S bend, and then there'll be a tower to hold this end of the cable. Okay, I'll be back in a few minutes and give you a progress report. Okay, here's that piece of 1/8 inch steel. It bolted in on those 2 bosses, just solid as a rock. Now we're going to build a tower of exactly the right height that can hold this end of the cable, probably a washer of some sort for this to go through and lock in place. Then the cable will come out of here and connect to the rod that I showed you earlier down here at this distal end. Now I made a vertical piece here with a 5/8 inch hole which will hold the end of the cable. The cable then will come out here and make a kind of a gentle S shape and go in through the firewall. I'm going to brace this now with a triangular brace and then weld it all together and paint it, and it should be very presentable. Here's that bracket for the accelerator linkage. It's all welded up, ground and painted. Now it's time to cut the cable to fit so that it'll make that passage from here to here. Okay, here's the plan. The rod has been cut to the right length to work with that cable and the cable end. I threaded the end of the rod so that the clevis that I made out of stainless steel with its captive nut can be adjusted back and forth about a 1/2 inch. Now that would be a good name for a band, Captain Clevis and the Captive Nuts. Okay, so now it's ready to be fit up to the carburetors and adjusted, and let's see if it'll work. And I drilled a small hole here in this end of the rod so I can put in a cotter pin so it can't fall out of that big control arm with all the holes in it. Okay, and they have a nice short 1/4 inch bolt here to connect the clevis to the cable end. Well, the linkage is all finished. I had to remove the tower piece here to drill another hole in it. I'll explain why in a second. But I took advantage of that to cut off that needless corner that stuck out over here. I thought this triangular shape was more pleasing, so I cut it, ground it, and repainted it. Okay, so what I found after I got it all together is that the return spring on just the primary carburetor was not strong enough to overcome the friction of the linkage and the cable. So I had to put in a supplementary spring, you see it down here, from the bottom of that arm here all the way back to an adjustable threaded rod that I have here with an adjustment nut in the back, so I can adjust the tension on the arm so that it will return the primary carburetor butterflies back to absolute idle rest position. You don't want that hanging open in the middle of traffic. Okay, so what I'll do, I'm going to get Ollie to get in the car and step on the gas, and you'll get to watch the linkage in action. Okay, Ollie, step on the gas. There's the linkage. It's all finished. It's fully adjustable as to travel and spring tension. Now all that's left to be done is the primary fuel supply right here, which will include the fuel pressure regulator, which hasn't come yet after 9 long and miserable days, and a fuel filter, a real nice one that you can disassemble and clean. Okay, so those two pieces are going to be right in here in series, and then we'll run the fuel line down and to the metal fuel line that comes from the gas tank. Well, miracle of miracles, the fuel pressure regulator arrived, and it's set right here at 2.5 pounds. There wasn't room to put the filter in back here, so I'm going to run the fuel line around over here, have the filter probably vertically right over on this side, and then we'll go down and connect to the steel fuel line from the tank. So this side here is officially finished. Just thought you might enjoy a quick little visual tour. And once I get the fuel line connected, I can pressurize the carburetors, and of course fuel will probably come flying out of every fitting, and then the Pertronix distributor will malfunction and start it on fire, but we can only hope. Okay, what a video that would make. Let's keep our fingers crossed, and let me finish up with the fuel system, and then we'll proceed. Okay, so now we have the Stromberg 97s installed on the engine with the fuel lines. We've got the adjustable linkage for the throttle, the fuel pressure regulator, and now let's take a look at where the fuel filter ended up. And it's right down here. Now I know that seems like an odd place, but it's very accessible there. I was thinking about running it back here behind the engine where it would probably never get changed or cleaned, but instead I ran the fuel line up, made a loop, and then went up to the carburetors and the fuel block first. But you can see it right down here. You can unscrew it. It's got the little sintered glass filter in there, and it's easy to get to and easy to change. One other thing that I added, because it's winter time here now, with temperatures, like I said, plunging down into the 50s, but I ran a choke line up here and then added a fitting, one of those little fittings that locks onto the ball ends that are on this type of linkage, and now I can adjust the choke from inside the car with just the standard old black choke knob, and it really helps starting up here in the cool weather. Okay, so that's it. It's all finished, and I have, of course, test driven it and made some minor adjustments, and what I'll do is start it up for you so you can hear it, and then we'll go for a ride. One other job I did on the car, which was long overdue, when I got it, it had no glass at all, and previously I'd put in the little quarter windows and a nice tinted back window here, but the roll-up windows was something I dreaded doing, but I finally did it. Okay, and it was even worse than I expected. As you can see here now, there's a nice brand new window roller, and the problem was that when they chopped the top, they destroyed the channels in the door that the glass passes through, and then they also welded the upper part of the door on crooked, so there was no way that a straight channel or a flat piece of glass could pass through it. So I had to reshape the doors and fabricate the steel channels by hand and install them here. They're welded in, and then I bought the 1/4 inch tinted laminated safety glass with brand new rollers, regulators, handles, everything. And what started out, what I thought would be probably a difficult but inexpensive job, ended up being a very difficult and rather expensive job. It was about $400, believe it or not, to put roll-up windows in the car. But I think it does sort of add an air of sophistication to it. Okay, so now it's time to start her up and go for a little spin. Okay, before we start up, I thought I'd take a quick walk around. Also, of course, we have the idiot with the leaf blower in the background who started the minute that I got out a video camera. Oh, I really like that old pinstriping. Okay, let's set up a tripod and we'll start it up and drown out that clown with the leaf blower. Okay, while the Lord of the Idiots drones away across the street on his second hour of uninterrupted leaf blowing, let's go ahead and fire this beast up. Okay, the door's open. Let's climb aboard and take a little ride out in the countryside. Okay, I got the camera on a tripod taped to the seat. So let's start her up and get ready for a ride. Well, here we are back home safely and in one piece. I hope you enjoyed the ride and this sort of supplementary video series on modifications to the engine in the 1930 Model A chopped-in channel coupe. Thanks for watching.